So, to start this video, I'll be going over kind of the background math with algebra and some geometry on how linear regression works. So to start out with, we'll make some data points. We'll make 3 data points on the x, y graph. We'll say about 1, 1.7, and 2.9, and then 0.5, 1.3, and then 2.7. And we'll go ahead and graph these. So 1, 1.7, and 2.9, and 0.5, 1.3, and 2.7. Alright, and we'll make our marks right here, and we'll say our best fit line is about right there. And so this is what our target is right here. This would be not really linear regression, but this is what we want to achieve with our linear regression with the least amount of error. And when I say least amount of error, I mean our actual data, or our actual y, minus our model. So, and that would be what we would define our error as. So we'll go ahead and use y equal mx plus b to help model this, and we'll say our y model is around our y value, so our y is 0.5, 1.3, and 2.7, which is around our y model, and this is equal to our x data, which is 1, 1.7, and 2.9. So that's our x times our, or not b, times our m, and plus our b, and our matrix here will be 1, 1, and 1. It's 1, 1, and 1 because both our x and y data still has a b variable, so this dot matrix can't be 0, and it can't be anything more than 1. So we'll use that, and we'll go ahead and simplify this down a little bit more, and this will be equal, and we can combine these two right here so we get them into similar terms. So we'll call this A, and we'll say 1, we'll combine our x and our b matrix, and we'll have 1, 1.7, and 2.9, and 1, 1, and 1. So we'll have a 3 by 2 matrix plus, or not plus, and we'll times by our constants m and b, and this will be our coefficients, and we'll just call it C, and this will be our design matrix. So the question is, how do we use this to minimize our error, or how do we get our error minimized? And so the best way to describe that is with a z, x, and y diagram. And we'll make up another kind of random example here. We'll just say that our vector here is 3, 2, and 1. So we have an x, y, and z is 3, 2, 1. And we'll say this is our vector, and this is kind of represent our actual data that we have up here. And we want to approximate this the best. So we'll use another matrix, and we'll say 3, 2, and 1. And we'll use coefficients and their unit vectors of x and y in order to approximate this. And so we'll use coefficient, and we'll use the unit vector of x, which is 1, 0, and 0. And we'll use 1 plus, and then we'll use another coefficient for the y vector, y unit vector, and that is 1, 0, 0, 1, and 0. And the reason we're doing this is because the best way to minimize error is for our actual data right here and our model data to be perpendicular to each other. We want them perpendicular because this line right here indicates how much error is between the two. So we want to minimize that and have this line be as short as possible between our actual data and our model data right here. So we want that minimized, and the best way to do that is with coefficients and their unit vectors. These coefficients allow us to kind of shape this line in order to make it perpendicular to each other. And because if C1 and C2 are too big or too small, it'll shrink this line down or make this line bigger, or it'll move it up and down, and this line will just get larger and larger either way you move. So we'll use these unit vectors right here as a model, and we'll plug it in up here to minimize our error with this. So we want our A value to be, or we want our unit vectors up here, this X and this, their B constants right here, which we use as these unit vectors right here. So we want this, the error between these to be perpendicular with the X matrix of 1.7, and 2.9, and with our B vector right here, we want to be perpendicular with E also. So we'll transpose this. So we'll transpose our A to be Y, and transpose it to be 1.7, and 2.9. We'll go ahead and label it AT real quick, and then we'll have 1, 1, 1. Then we'll multiply this by our error, and since these are perpendicular to each other, we'll take a dot matrix of it right here. This is going to end up being equal to 0 right here. So we have AT times our error is equal to 0. So we'll go ahead and plug it in. So we'll have this actually is equal to 0. So we'll go ahead, we defined our error earlier, so we'll go ahead and plug that in. So AT, then our actual data minus model data is equal to 0. So we'll use this to decrease or to minimize our error and use our y equals mx plus b in order to do that. So we have AT actual data minus model data. We'll go ahead and distribute that out. So I'm gonna move over here. So our AT times actual data minus AT model data, and we already defined our model data also right here. So we'll go ahead and plug that in, and our actual data we said earlier was this y. So we'll go ahead and plug these all in, and also define our AT right here. So we have all these, so we'll go ahead and plug these in right here. 1, 1.7, 2.9, 1, 1, 1, and our y values, which are 0.5, 1.3, 2.7, and then that is equal or minus the transposed matrix again, which is 1, 1.7, 2.9, 1, 1, 1. And then we have our y model, which is our A, which is 1, 1.7, 2.9, 1, 1, 1, and then our coefficients, which are A, M, and B. So, and this is all equal to 0. So we have two unknowns now, and we plugged in two equations currently. So that is what we'll use, and we'll move this on to our Python in order to solve it farther and get our numbers. Okay, we'll be going over our Python for homework 1 part A, or part 1 now. Homework 1 part A. So we'll use our X data. In our problem statement, it wanted X to be linearly spaced from 0 to 10. And it wanted evenly spaced 21 times, so we want 21 points. Enter. You can check that. Shift enter. So there's that, our evenly spaced X's. And then we have our once graph of a slope of 2x and then plus 1 for our intercept. So once a slope of 2 and an intercept of 1, and with plus on that, or not plus, times. Okay, and then it wanted the y's to be standardly deviated by 0.75 around that slope intercept. So you can do that by doing y equals y plus np dot random dot normal, np dot random dot normal, and we wanted it to be at the 0 of the array, and we want the scale to equal 0.75, and we want it to be the size of our y, so size, and then dot, or equal, and then y dot size. Damn it, what happened? Alright, y dot size. Okay, and then we can check our y right here, shift enter, and there it is. There's our standard deviated data, and we can make sure by making a graph real quick. I have to make one anyway later, so we can go ahead and make one right now and make sure. Sub plots, and then open, and then fig dot add scatter, and yeah, we want our, that looks good. And then shift enter. Oh wait, hold on, we want markers, so let's remove that, and then mode, and then equal markers. Yeah, that should be fine. Then shift enter. Yeah, so there are markers. The standard deviated right there. So we can move on. So we need to find our A, which is with our design matrix. So we want to define that. So we have A, and it's equal to np dot c underscore, and then we have our brackets because it's an array. So we have x in one column, and then we want our ones in the other. So the way we can do that is np dot ones underscore like x. Okay, and then we can check A, make sure it's all right, and then shift enter. Yep, so we have our x values and our ones right next to it. So that looks good, and then we can move on to solving our equation. So we have on the left side we have our A dot t transposed, and we want to multiply that by our y. Actually, we'll do the other side first. At our A, so we had the A on the other side, our design matrix times our C, our coefficients. So we'll just do AT times our A matrix for right now, and then we hit shift enter, and yep, it should be a 2 by 2, so that looks good. And then we have our AT, and this should be I think it should be a 2 by 1, if I'm correct. And then we have our y, and then we'll make sure on that, shift enter. Yeah, okay, 1 by 2, yep. So that's good. And then we can do solve for our C, which is np dot our linear algebra. So lin alg dot solve, and we want so it has it there for us already, our AT. I don't want to print it though. Yeah, I can't see if it's right or not. Wait, yeah, that's right. Okay, and then we can unpack our C from our array, so M and our B. Well, actually, we'll see what C equals first. So C, shift enter, or wait, whoops, capital C. So C, shift enter. Yeah, so this is our M and this is our B, because that's how we had it in our formula. So we'll have to get those out of the array, and that's pretty easy. So we do M and B equals our C, and then we can make sure we have our M and B, shift enter. Yep, so now they're floating, so that's good. So then we can take them down here, and we can make it into a line. So we have fig dot add underscore scatter, and we want our x's to be our x's still. So x equals x, but now we want to model these y values after that line. So with our new M and B that we have, so y equals M times our x, and then plus our b, and then we want our mode to equal our lines, and then we can just name it So we have that. It's not gonna like something right here. Maybe. I don't know. Oh, do I need the? Yeah. What's going on here? Perhaps you forgot a comma. Oh, right here. Okay. Okay. Yeah. So there's our linear regression, and we have it. And we're comparing it to our deviated data. So that is it, and we did that by getting our formula from our matrices and using the unit vectors that we had, and we used Python's linear algebra solver to get our M and B, and we unpacked them and we plugged it into our scatter plots, and that's it for the Python.